Okay, this is activity 2.1.7, calculating truss forces. And I wanted to show you how to do a couple problems here so that you can finish this while I'm gone. On problems 1 through 3, there's really not a lot of work to do on those. On problems 1 through 3, those trusses are statically indeterminate. In other words, those trusses are really not any good. And what they want you to do is to use this formula 2J equals M plus R to demonstrate that those trusses are statically indeterminate. So you're just going to show that those won't work. Once you show that those won't work, then go ahead and sketch a solution that would make those trusses be statically determinate. So I'll show you number 1, and then you guys can do numbers 2 and 3. So here on number 1, we know that our formula is 2J equals M plus R. J is the number of joints, so we'll count those. That's 1, 2, 3, 4 joints, so it's 2 times 4. M is the number of members or beams, so we have 1, 2, 3, 4, 5 members. And R is the number of reactionary forces. So we have 2 pins here because these are rollers and these are pins. So I have 2 pins, and remember that each pin has 2 reactionary forces. So there's one in the Y direction, one in the X, one in the Y direction, one in the X direction. So each one of those pins has 2 reactionary forces. So that would be a total of 4 reactionary forces. So 2 times 4 is 8, and 8 does not equal 9. So this truss is statically indeterminate. So we've shown that it's statically indeterminate. We now need to fix it so that it would actually work. So I think the easiest thing to fix on this one would be to make this side into a roller, so that it would only have 1 reactionary force. So when we turn that into a roller, we would still have 4 joints and 5 members, but now we only have 3 reactionary forces. So 2 times 4 is equal to 5 plus 3. So this one is statically determinate if we change that one thing about that truss. So you go ahead and try numbers 2 and 3, and that's all you have to do on those first 3 problems. When you get to numbers 4 and 5, we're going to actually calculate truss forces like we've been doing this week. And I've made a note page that has number 4 bigger so that we can work from there. So we'll come down here and actually look at our note page. So this is number 4. So remember that our first step is always to find our angles. So I can tell that angle A is 90 degrees. And I need to find angle B and angle C. So angle B would be this angle up here. And I know that its opposite side is 3 feet, because this up here is 3 feet. This down here also has to be 3 feet. And I know that its adjacent side is also 3 feet. So I can use my trig function tangent to find the measure of angle B. So inverse tangent of 3 over 3 is 45 degrees. So angle B is 45 degrees. Because all of these angles in a triangle have to add up to 180 degrees, then the missing angle is also 45 degrees. So both angle B and angle C are each 45 degrees. Now you may have known that without doing the trig because both of the legs of your triangle were equal to each other. So that means that their angles are also equal to each other. It's an isosceles triangle, an isosceles right triangle. So once we have found our angles, and at this point, if you want to stop the video and then do the angles for number 5, that might be helpful. And then we'll go on to the next step. The second step is to find your outside reactionary forces, applied and reactionary forces. So we're going to find all of our outside forces. This problem is a little different than the ones we've been working on because our pins and rollers are on the side. So that's the reason I wanted to show you this. So I'm going to go ahead and label again what we know about our angles, 45 degrees, 45 degrees. So I'm going to list all of my outside forces that are in the x direction. I know that those have to add up to be 0. I'm also going to list our outside forces in the y direction. I know that those are going to have to add up to be 0. So I've got an outside force right here at angle C, and that one is an outside force of negative 50 pounds because it's going down. Because angle A has a roller on it, it's going to have an outside force. Normally we would put that this way, but because of it being on the side, I actually have to put it in the x direction. So I'm going to have an RAX, and I don't know that force. Then at angle B, I'm going to have an RBX. I don't know that force. And I'm also going to have an RBY. And I don't know that force either. Now remember that we know that our moments clockwise have to equal our moments counterclockwise. So our force clockwise times our distance clockwise has to equal our force counterclockwise times our distance counterclockwise. So remember, we need to set our pin, this one right here, we're going to set our pin. It's not going to move. Then we've got to determine if what our other outside forces are going to make this truss do. So if I pull down at joint C, that's going to make our truss move in the clockwise direction. So that force is 50. The distance back to the pin, even though you don't want to go diagonal, I know our pin is here, but we just think horizontally from joint C back to joint B, it's 3 feet. Then at joint A, if I push on joint A in this direction, it's going to make everything go in the counterclockwise direction. So I don't know that force at joint A, but I know that that distance to the pin is also 3 feet. So 150 equals 3x, divide by 3. So that force at joint A is 50. So this is 50 pounds. That makes, because these have to add up to be 0, that makes RBY, the reactionary force at joint B in the y direction, positive 50 pounds. And that makes the reactionary force at joint B in the x direction negative 50 pounds. So we really need to change our arrows at joint B because in the x direction I should be going to the left, in the y direction, I should be going up. Both of these are 50 pounds. So we have found all of our outside forces. So once we have found our outside forces, then we're ready to go ahead and do step 3, which is to find the forces of all of our members. Go ahead and erase this step. Again, if you want to pause the video at this point and do the outside forces on number 5, it might be beneficial for you to take this step by step instead of watching the whole video. So step 3 is find the member forces. And we do that by doing free body diagrams of all of our joints. Okay, so I'm going to start with joint B. I kind of skipped A because joint A has a 90-degree angle, so I'm going to skip joint A and then just move right to joint B. So if we take a look at joint B, I want to draw everything that's associated with joint B. So I've got those two members, and then I've got an outside reactionary force and another outside reactionary force. So I'm going to draw that over here. Here's B down to A, then B down to C, and then I've got a reactionary force going up 50 pounds, reactionary force going left 50 pounds, and then I'll need to find BA and BC. So I want to list, at this point I want to list my forces in the x direction and list my forces in the y direction, and keeping in mind that I also have to find any diagonal members, and the only diagonal member or beam that I have is BC, so I'll need to definitely find that beam. So I'm looking for anything that goes left and right. So I've got this outside force at joint B that goes to the left 50 pounds, so I definitely have that one. The only other force that I have that goes left and right is the component force of BC. Remember, since BC is a diagonal line, it has an x component and a y component. So I'm going to go ahead and write the y component down. So we don't know either one of those. Now let's look for forces in the y direction. I have BA that's in the y direction, and I also have the outside force at joint B right here that's in the y direction. And that one we already know is positive 50. So I can solve for BCX really easy because I know that that should equal 0 if I add these up. So BCX has to be positive 50. So remember that this angle is 45 degrees, which makes this angle also 45 degrees. So if I solve for this component, BCY, this is BC in the y direction, I'm going to do the tangent of 45 equals, the opposite side is the one I don't know, BCY, and over the adjacent side, which is 50, that's BCX. So I cross multiply here, tangent 45 times 50 is equal to BCY. So BCY is equal to 50. Positive. Oh, that would be negative 50 because this BCX is to the right, so it's to the right and down because this is going down, so that would be negative 50 for BCY. That one, this one, negative 50 for BCY. So if all of these have to add up to be 0, negative 50 plus 50 is 0, which makes BA exactly 0. So that one is 0 pounds. So there's no tension or compression on that member. So that's joint B. So we have found that BC is going down, which makes this one go the other way. But we just don't know this number in here. So we still have to find that. So that's the reason I always list this diagonal member so that I don't forget to do that. You can use Pythagorean theorem, or you can use any trig function you want to here. I'm going to erase this over here. So the trig function that I'm going to use is, I'll probably just do tangent. Tangent of 45. Oh, not tangent, because I'm trying to find the hypotenuse. Let's do sine of 45 equals the opposite, which is 50, over the hypotenuse, which is what I don't know, which is BC. So I'll cross multiply. Sine 45 BC equals 50. Divide by sine 45. So if I do 50 divided by sine 45, it will equal 70.71. So BC is 70.71. So right in here, this is 70.71. Because those are pointing away from the joints and toward the number, that is in tension. So that joint is in tension. That member is in tension. Remember, we already found this one is 0. So the only one that we need to find still is CA. So we'll take a look at joint C and see if we can find CA. So we're still on step 3. We're just going to do joint C. Okay, so if I draw joint C, it's going to look like that, and then you're going to have an arrow there. So I've got joint C. Here's C, here's A, and I've got a force going down, 50 pounds. I already know that this one is 70.71. So our forces in the x direction are CA, which I don't know. This was B up here. CB in the x direction. That's this component. So this is CB in the x direction. Our forces in the y direction are joint C had a negative 50 pounds, and then CB in the y direction. And that would be this leg over here, CB in the y direction. So real easy to find CB in the y direction. That's going to be positive 50, and that equals 0 because the sum of those have to equal 0. Now CB in the x direction, since this is going up, that means this vector is also going up, and it's going up and to the left. So that makes CBX negative. And we found BC in the x direction a minute ago, and it was positive 50. So if BCX is positive 50, that means CBX is negative 50. And that's working out for us because this vector is going up and to the left, so it has to be negative 50. So that makes CA really easy to find. We're not going to have to use any trig at all on this one. Since our forces in the x direction have to equal 0, that makes CA positive 50. So CA will be going to the right 50. So on our diagram, it's going to the right this way, that's 50. And that means this way it's going to the left. So that means because they're pointing at the joints, that's compression. So that should be all that you need on number 4. So you can try number 5. Hopefully you've been stopping the video and working each step as you go.